Hi, everybody. I don't know why the screen is so dark today, but thank you for coming on and watching this video today. So what we are getting into today is parametric equations. So I'm going to show you the warm-up, which is right here. So go ahead and take a look at that. A raindrop's position depends on time each second and moves 1 inch east and 10 inches down. Complete the table. Go ahead and take a moment to do that. And hopefully you got a horizontal position continues just counting by ones, 3, 4, 5, 6, 7, 8, 9, 10. And the vertical position keeps counting down by 10. So 70, 60, 50, 40, 30, 20, 10, and 0. So before we talk about why we did that warm up, today we are eliminating a parameter and recognizing function types. So we have a warm up, some examples, and then a check for understanding. And then don't forget about your week 2 and week 1 things as well. What is a parametric equation? So in math, a parametric equation defines a group of quantities as functions of one or more independent variables called parameters. So instead of just dealing with y equals x or y equals x squared or our normal what we call rectangular functions, the idea of a parametric is that there's another independent variable that's acting on y and x. Y is still often a function of x, but t is our new parameter, such as time. So let's review the raindrop example. So we had our height and it started at 100. So the height of the raindrop started at 100 and our horizontal position started at 0 and ended at 10. But in this case, what we have is actually a parameter time t, which kind of indicates the order in which these things are happening, but the fact that we start at 100 and we end at 10. So the arrows that are appearing here just indicate the direction of the graph, because we have this third variable time that is the independent variable for both x and y. So in addition to just that function x and y, the two variables x and y, we have this third variable t that's indicating, okay, when in time is this happening? Okay. All right. So we're going to do some examples of how we eliminate the parameter and state the type of rectangular function. So the typical way that we do this is we just solve the x equation for t and then substitute that expression into the y equation for t. So you can see on the upper left here, there's two parametric equations, x equals t plus 1 and y equals t plus 1. So this is all one function, right? It's just that the parameter t is acting on both x and y. I like to think about the raindrop example because I like to think about time being the independent variable for x as horizontal motion and y as vertical motion. Now, parametric equations can model any other thing, but that's the easiest way to think about it for me is just a vertical, horizontal, and then t is that third variable that indicates maybe time, right? So each second, your object's moving one space to the right, and each second, your object's moving one space up, for example. Right, so we're going to solve the x equation for t. So we get t equals x minus 1. And we just subtracted 1 from both sides on that t equation. And then we take x minus 1 and substitute in for t in the y equation. Right, so now instead of y equals t plus 1, we have y equals x minus 1 plus 1. And then we can simplify that, and that'll just be y equals x. And if you think about the line y equals x, that makes sense with the way that this function is being impacted by time, right? Each second or each unit of time, our object is going to move one space to the right and one space up, which is exactly what the equation y equals x is doing. The difference with time is now we have this direction, right? We know that we're going northeast, if you will. Okay. Okay, so here is an example on the right. We have x equals t over 2 and y equals t squared. So again, we'll solve that x equation for t first. So multiply both sides by 2, and we get 2x. And we substitute that 2x equation in for t. So we have y equals 2x squared, which is y equals 4x squared. And one thing I didn't say about this is that it does say eliminate the parameter and state the type of rectangular function, right? So y equals x is a linear function. We recognize it because it has a degree of 1. And 4x squared is a quadratic function. We recognize that because it has that degree of 2. Go ahead and try these. And then this is your result, 2 linear functions. Okay, there are some other examples that we could do. Basically, we're still solving your x equation for t and substituting it in for y. It's not just linear and quadratic that are possible. You could have an exponential function. You could have a square root function. You could have any type of function. But then I also wanted to show you how with this particular set of parametric equations, you can also use the y equation, right? So y equals 5t. Sometimes that might be easier. Divide both sides by 5 and then substitute that y over 5 into the x equation. So it's kind of up to you. You can use your discretion, but we won't really be doing this week because we only have 1 week to do parametric functions. I just wanted to show you, one, there are any type of function could be modeled by a set of parametric equations, and then also sometimes you could use the y equation and substitute in for x if you wanted to. Okay, the next piece of this is conic sections, and I see that I still have the word function here, and I don't mean rectangular function, I mean conic sections. So here we have x equals cosine of t and y equals sine of t. So whenever you see a parametric equation that looks like this with cosine and sine, it's probably going to be, at least in this unit in this week, a conic section, a circle, ellipse, hyperbola, or parabola. And honestly, again, since we are very shortened with this unit, we are most likely just going to stick with circles and ellipses. So here are the steps with this one. I'm going to do the one on the left first. So the one on the left, you have x equals cosine t, y equals sine t. And we want to get it, we want to eliminate the t's, we want to eliminate the parameters and just have everything in terms of x and y. So the first step is to square both sides, and you'll see why in a moment. Okay, so we have square both sides. And then we're going to rearrange the equation, right? Because this is in terms of t. T is the connecting variable. We can say that x squared plus y squared equals cosine squared of t plus sine squared of t, right? We recognize cosine squared of t plus sine squared of t as a Pythagorean identity. So that just leaves us as x squared plus y squared equals 1, which I'm hoping you all recognize from geometry as a circle with a radius 1. On the right, now we'll move to this one. We have x equals 2 cosine of theta, and then y equals 3 sine of theta. Now, these coefficients are different. So we're still going to square both sides. Oh, I had a little graph of that circle for you. Okay, so we're still going to square both sides, just like we did in the circle example. So that'll leave us with x squared equals 4 cosine squared of theta, and then y squared equals 9 sine squared of theta. But because this is these coefficients are different, before we try to use the Pythagorean identity, we're just going to divide the coefficients on both sides of the equation. So that gives us x squared divided by 4 equals cosine squared theta. And then y squared divided by 9 equals sine squared of theta, right? Because we want to have a very clean Pythagorean identity when we rearrange the equations. We don't want to have the 4s and 9s on that right side there. Okay, so we rearrange just like we did in the first example. And bam, Pythagorean identity, cosine squared plus sine squared is 1. And then because those coefficients were different, this is an ellipse, right? And this is actually what that ellipse looks like. So pretty cool. We can use sine and cosine and Pythagorean identity to rearrange our parametric equations into rectangular equations. And we don't call these functions because you have more than one input for most of the x's here. So we're going to call them relations, which is why this rectangular function piece here is an error on my part that I'll go back and fix in your notes. All right, go ahead and give this a try. Pause the video, try the problem, pause the video, try the problem. All right, so now hopefully we got that on the left side, we have this ellipse, x squared over 4 plus y squared over 16 equals 1. And the right side, we got a circle, x squared plus y squared equals 9. And that's a circle with radius 3. Okay, so the last thing I want to cover is using technology. So I'm going to first, let me unshare my screen. I think that my Zoom controls are on the other side of my desk, so I need to probably fix that and see if that is indeed what's going on. But so the parametric equations are doable in both the TI-84 graphing calculator. So if you're using that app, that's great. And they're also doable in the in Desmos, right? So here on the slide, I have both. I have TI-84 and Desmos. So with the TI-84, and I'll show you this in a minute, I'm just having trouble getting my Zoom shared screen under control, but you wanna go to mode and you wanna go to parametric, and then you can just adjust your window to however you want the window to look like, and then it'll just straightforward graph it for you. Right, so in Desmos, and there, I'm going to post a video for this. This TI-84 link here is actually a YouTube video that you can go, it's short, it's 1 minute, you can go back and look at it. And then with Desmos, I might put in a video later, but you just want to type in, oh, here's my screen share. You just want to type in the expression for each parameter as though it is a point. All right, so let me move, that's where my screen share was, good times. I'm going to move to my TI-84 and share this now. So here's our TI-84. We want to go to mode, and we want to go down to function, and we want to change it to parametric, right? And then we can go to y equals, and now that xt theta button that in your whole, probably your whole math life has just been an x. Look at that, now it's a t, right? So you can put in whatever parametric equation you want, t plus 1. You can do the one we did earlier today, t plus 1, t plus 1. Look at our window. I mean, you can just make the window whatever you want. I think I'm going to see how, if I can just go -10 to 10. And then my t step can be 1. And I'll just hit the graph and look at it. And there we go. Beautiful. Y equals x, right? So again, mode, pick parametric next to function, y equals, and it'll be in parametric mode for as long as you need it to be. Okay. Now I want to show you how to do it in Desmos. So in Desmos, it's a little different. So basically with Desmos, you're just going to type the equations in as though they are a coordinate point, right? So if you type in a coordinate point like 1, 1, it'll just label that on the graph. So what you're doing is you're typing your parametric equations the same way. So we could do t plus 1, comma, t plus 1, comma, t plus 1. And what's cute about Desmos is it puts your domain in for you. So you could just put your domain in however you want. So we could do -10 to 10. Or in the case actually of your trig functions, so if you had cosine t, sine t, I need to put the parentheses around, that's important. Cosine t, sine t. If you notice that if you don't go all the way around to 2 pi, it only graphs like a part of it. So from t equals 0 to t equals 1, it only graphs a part of it. But if you go all the way around to say 2 pi, you'll see a complete circle there. So that's how you would graph it in Desmos. So I hope that helped. That's really all I have for you today. Just make sure if you are one of my students, you complete your check for understanding and complete your homework. Thank you so much for watching, and I hope you have a great day. Bye.